So it actually just went up. It's 789 now. Okay, so what kind of chips am I testing? Obviously not these kinds. Oh, oops. Well, you know what? I gotta display. Okay. See if this thing works. All right, well, I'll just use the keyboard. Okay. All right, everyone ready? So I'm Evie. Hi. Okay, so what kind of chips? Not these ones. So dual integrated package is what I test. The chips have 8 up to 48 pins. The width of the package is 0.3 inches up to 0.6 inches. I test currently digital outputs only. The power rail of the chip can operate at 3.3 volts or 5 volts. And you can see there's a SIM adapter there. So adapters can let you test packages other than the DIP. These are these are the best organized chips in my collection. The rest are just in bags. Okay, so does anyone know why you should test chips? Okay, anyone else? What was that? Okay, so they work or they don't. Anyone else?
Because most of us have soldered chips in without testing them and found out why.
Okay. Anyone else?
Make sure you know what you wanted.
Okay.
How about to verify the chips you bought are really the chips you bought?
Okay. All right, so I'm going to go into my reasons. Repairing vintage machines. This is why I got started with testing chips. Some people like to build retro-inspired machines. You might want to catalog or sort your collection. You might want to buy and sell chips, and it helps to know if they work, or if you got new chips, do they work? Do you have fakes? Do you have variations? Maybe, my other reason is I just wanted to learn, like, what do all these chips do? Okay, this was my first chip tester. It was first available about 4 years ago, and I made it with a Teensy 3.5. I guess you can't get them anymore, but it was like one of the last 5-volt Arduino compatible platforms that had a lot of IOs on it. And so you can see there's little jumpers, those columns of blue, black, and red. You have to manually route the 5-volt power. So then I came out with a new version, the Pro version, I call it. And this time I abandoned the Arduino API. I'm using a STM32 ARM Cortex-M processor, and I wrote my own bootloader so that you can update the firmware with an SD card. You don't have to plug this into your computer. And then I put a better socket on there. It's a normally closed socket, and that means that you have to apply more pressure to open the socket than you do to close it, so it has a stronger connection. And then I also put voltage and current limiting in there, which makes the tester pretty bulletproof so that you can't fry it. Okay, and then about a year ago, I made the Pro V2, and you can see it's got 2 more of these ARM Cortex chips. The 2 extra chips I'm actually just using as multiplexers because it turns out that they're just very efficient multiplexers if you don't need instant switching. And then there's no jumpers. The power routing's automatic. And to actually route the power, it uses those multiplexers and uses transistors to route the power. Okay, so what is logic? This is people interested in this probably already know most of this basic stuff. But at its most basic, logic is inputs and outputs from the chip. It is read as a low level, around 0 volts, as a high level, or a value 1, and that's going to be on the high end of the voltage. And then floating high Z, which is high impedance. That just means that the logic is disconnected, and it might be kind of unpredictable. Okay, the most basic type of logic is unary, 1 input, 1 output. So you can see on the upper left a buffer. It just takes an input, and the output is the same thing. And that can have a lot of uses to strengthen the signal, to protect one device from another. And then there's the NOT gate, which takes a high, makes it low, and vice versa. Okay, and then going slightly more advanced, binary logic, 2 inputs and 1 output, and the main ones are AND, OR, and XOR gates. AND is true if both inputs are true, OR is true if either input's true, XOR is true if one input is true but not the other. And then you might have heard of NAND gates, NOR gates, or XNOR gates, and that just means it adds an inverter on the output. So then, more complicated than that, there's bistable logic, which is essentially like memory or a register. It's a value that gets stored that then doesn't change. And so it's a memory state, and that's why it's called bistable, because it can be stable at a high level or stable at a low level. And then even more complicated than that is synchronous logic, where you can trigger a change based on the change of the input signal. So if the input goes from high to low or low to high, then some change occurs. And that's also called clocked. Okay, if you go on Wikipedia, you'll see these are the common digital logic families that have been used over the past 70 years or so. Except for the purposes of this talk, I'm only going to focus on TTL and MOS or CMOS. That's transistor logic, or metal oxide semiconductor logic. Okay, these are pictures cut from some advertisements from Electronic Design magazine. And Texas Instruments was the most successful, most popular maker of TTL chips. And RCA came on the scene, and in the mid-'70s, their CMOS chips started to get some adoption, some share of the market. They initially called them Cosmos, and I think that was related to their Cosmac ELF machine. So the most common series of the TTL digital logic was the 7400 series, and the most common for the CMOS was the RCA CD4000 series, or sometimes just called 4000. So if you use my chip tester, the first 2 menus are just, here are the 4000 series chips, here are the 7400 series chips, because those are by far the most common chips. Okay, now this is showing you how logic is interpreted by the chip tester. TTL, or transistor logic, registers as low if it's below 0.8 volts, registers as high if it's above about 2 volts. Now this is when you're using it as an input. As an output, I think it expects values slightly outside of those ranges, and then of course in a real world use case there's going to be noise and things are going to change. So ideally ideally a TTL chip will output close to 0 volts and will output somewhere around 3 volts, or maybe it might even output 5 volts, particularly if you're using a 5-volt system and it's running open collector. then you might just get a 5-volt signal for your high input. The chip tester logic is different because it's using essentially modern 3.3 volt CMOS type. Don't quote me on this, because it's actually what you see on the microprocessor is you see the logic running at 3 volt. Internally, it's probably running at a lower voltage, but I'm not gonna go into that much detail. So the chip tester logic, when I read the digital logic coming from the chip, you can see that the values registered as low are pretty close, 1.2 versus 0.8 volts, and then the high, 2 volts versus 2.3 volts, and then there's the gray area in between. So most of the time, it can input TTL logic just fine, it can output TTL logic just fine, and then you can see between 3.3 volts and 5 volts, I say tolerant because essentially the chip tester will never output more than 3.3 volts on the I/O, but it can receive anything up to 5 volts without breaking. Okay, now this is the CMOS logic, and you'll notice CMOS reads low between 0 and 1.5 volts, reads high between 3.5 volts and 5 volts, and this is assuming the CMOS is operating at 5 volts. And then, so you can see on the low end, it matches up okay with the chip tester, 1.2 to 1.5 volts. But on the high end, the chip tester, it can receive 5 volts, and it's okay with that, but it can only output up to 3.3 volts. So the CMOS, that registers as a gray area. So I can't reliably output a high level to a 5-volt CMOS chip. So the workaround for some chips, if I run the CMOS chip at 3.3 volts, then it actually matches up pretty well. And so, actually, before we go there, so this works in most cases. The one major exception is the early RCA processors. They will only run at 5-volt CMOS. The RCA logic chips will run at 3-volt CMOS. So there are some chips that the current chip tester doesn't support, and in my next revision, I'm aiming to support those using level shifters so that I can interface with true 5-volt CMOS logic. Okay, so now how do you know if a test is accurate? Does anybody have a gut sense of how do you know if a test is accurate? Okay. Anyone else? Exhaustive paddle testing. Pattern testing, okay. So this obviously is a joke. Trust me, I know what I'm doing. I mean, as much as you have faith in me and my product, that's how accurate the test is. The accuracy that I can make the test is limited by the sample size, so it's limited by how many chips I have, how many people I have that have reported results. Obviously, you can cross-check with other tester hardware, and a lot of my users do that, and that helps me improve the test. You can perform a real-world test, stick it in a machine that it's supposed to work in, and does that machine work? But what I've found, my biggest lesson in working on the tester is if I can give you more information, then everybody can get to their solution faster. Everybody can know a little bit more about what's really going on. If there's a problem with the test, if there's a problem with the chip. So here's a chip. It's a 6502 processor variation. It's called the Sally. It was used in Atari 8-bit computers and their 5200 game system. So let's say you test this on the chip tester, and you get these individual results. The clock passes, logic passes, int fails. So one possibility is that maybe the interrupt output isn't working, or maybe there's some kind of problem with the register storage. So having more information helps you to zero in on what the problem really is. And then also I can offer information like I can detect what variation of a 6502 is this. So the Sally versus the regular 6502, the read-write pin is in a different place. So if I run the test with the read-write pin in one place and it passes and it doesn't in the other, then I know what variation it is. Okay, so these are some ideas I have for the next hardware revision of the chip tester based on the issues that my users have had and the chips I want to test that I can't check. So I want to support multi-voltage chips, and these are chips that are going to require having like 3 different voltages input. So one of the most common is a DRAM chip that requires -5 volt, +12 volt, as well as the 5 volt and ground. And I have an adapter for that. But if I was going to make an adapter for every single chip that has different voltages, it would be too many SKUs, and I like to generalize things. I like to simplify the process of testing so you don't have to have 50 adapters. So to support all these different voltages on one device, I'm envisioning using relays, probably physical relays, just because, I don't know, I just like the clicking sound. And the nice thing about having a relay is that you can switch the pin of the chip between the I/O of the tester, which needs to be between 0 and 5 volts, and the power of whatever the input is, anywhere from -12, maybe even 24 volts for an EEPROM. I want to offer true 5-volt CMOS support using level shifters. I want to have an analog input, and I want to put a FPGA in there so I can have real-time analysis down to a small amount of nanoseconds. And this goes with the idea of just having more information. And then another idea I have is to do user-definable tests. And this is because I'm limited by my sample size, I'm limited by what I have on hand, what chips people are willing to send through the mail, and not knowing if they'll get to me. And so I'm thinking about making some kind of language, and this is actually quite compatible with my progress with the chip tester, because my tests, doing so many tests, the commands I use in my code have become almost like a scripting language. So based on my experience and how I write tests, I want to try to translate that process so that other people can write their own tests, and then, hopefully everyone benefits from that. Okay, so this is the general process of how I write a test. So first thing, get the data sheet. Nothing is more useful than the data sheet when writing a test. If you can't find the data sheet, at least get a pinout. Assign the power and ground pins, and those will be listed as VDD, VSS in the data sheet, etc. Configure the inputs and outputs, and the tricky thing is that the inputs and outputs of the chip are opposite of what the tester's inputs and outputs are, because the tester outputs to the chip's input and vice versa. I want to apply a master reset. If there's a reset pin on the chip, I'll want to activate that so it's in its default state. I want to apply a clock input to the chip, so in particular, like microprocessors need a clock. Most microprocessors are okay with slowing down the clock to a very slow speed. Some are not. And this is another application for doing FPGA-based tests. The FPGA-based test could be a real-time test. It wouldn't have to slow down the clock. A really interesting thing I've learned from studying a lot of data sheets is often the crystal layout in the data sheet is actually inverted between. So the crystal operates usually with an output to send to the crystal and then an input from the crystal, except the way that I'm controlling the chip, I'm only using the input. I'm ignoring what's being output because I don't need the tester to be driven. And for whatever reason, these are often reversed in the data sheet, and I'll have to flip the pins in my code. And okay, so if a chip is a simple logic chip with no registers, no states, I can just loop through all possible inputs and verify that the outputs are correct. If the chip has internal registers, internal memories, I want to assign those registers to all possible values, and then also find the outputs for each set of register values. Now, this can get exponential very quick. You might have millions, you might have billions of combinations. So if there's billions of combinations, it might be wise just to skip a few, because you probably don't need to test every single combination to find out if there's a flaw in the chip. If there's a lot of buried logic, so like a microprocessor, a video chip, an audio chip, might have a lot of buried logic, meaning like registers internally that affect other registers. So I try to write at least one test for each input or output pin, and that usually catches issues. A lot of chips die by just being totally melted down, or they die by one pin being burned out. It's probably possible, but less common, that maybe some internal register of the chip gets broken. Another thing I can do with tests is pin mutations. So if a chip is the same chip but it's in a different package, like if you have a DRAM chip that's in a DIP package, and then you have the same DRAM chip that's in a ZIP package where the pins are arranged like in a zigzag right next to each other. Usually the pins are different, but there's actually a predictable pattern to go from one test to the other test. And so you can have the same test and just have it reassign the pin out. That can be really useful. Also with PLCC chips, they might be the same as a DIP chip with just a different pin out. And so also regarding the buried logic, so I only have the ability to spend so much time on each test, and if I have an open user-definable language, it's possible that people with extra time on their hands might drill down and make even better tests. And I think that also helps out with the confidence that the tests are as accurate as they could be. Okay, so call to action. I retired. I used to be a software engineer in the games industry. I retired from as a software engineer in 2018, just with a number of life changes, and I just wasn't really compatible with being managed anymore. And I kind of went on a vision quest, and that led me to doing a YouTube channel. And so you can find that on my website, backbit.io, or Evie's, revue.com. I haven't done a video in probably about a year. I'm always open to doing videos. I just haven't been really motivated, and I've been focused on building products and shipping them. But I've been doing retro hardware since 2019, and back in 2019, I knew almost nothing about electronics. I knew plenty about software, but almost nothing about electronics. So I've learned a lot over the years, and I want to keep learning. The goal with my products is to not be salesy. I just want to make things that people want and try to provide a good value. I have a lot going on now. I have a new cartridge in development for the Neo Geo. I want to make the next chip tester revision. So I'm a little bit overwhelmed, and this leads into the next part. So writing tests by myself, I have to have the chips on hand. I have to spend the time. I don't really mind spending the time. It's more of an issue of having them on hand. So this really lends to, I want to make this open testing language. But I have tons of ideas, and maybe not always the best image of reality. And so I am looking for people to collaborate with, not necessarily like work with me full time, but just people who are curious about my products or think they should be a certain way, I'm really open to ideas. And human interaction's my fuel, so you can talk to me about whatever, talk to me about music, talk to me about nerdy things. This whole project is kind of open-ended, and it's kind of just based on what the demand is, what do people want to do. So I'm open to questions. Yes? Do we have a microphone for questions? No? We don't have a runner? I guess not. Okay.
I'll be loud.
All right.
What's a test look like in software? Is it written in C? Is there a bunch of macros?
Yeah, so I write my tests in C, but over time, those C commands have been more consistent between tests and just, this is going to contribute to what the testing language is. So a lot of my tests are just command, like test mode of this pin is input or output, read this pin, write to this pin, check if this pin is floating.
Your burn-in functionality is really useful for finding the bugs too.
Oh, burn-in?
Yeah, is that like part of the testing framework? Like, you just like you can always move everything? Or?
Yeah, so for every test, there's a couple options you can configure. You can set it to a burn-in mode where it just runs the test, runs it again, and keeps going, and it'll tell you how many times it failed. And then another thing you can do is change the vertical offset of the test, which is kind of a relic from when I was doing a little bit of in-circuit testing, where you can just move the chip down in the socket. It was mostly useful for in-circuit testing, but also if you just want to see if there's something wrong with your socket. Anyone else?
What clock speed do you use for testing, or is it
So
slow?
the STM processor runs at about 280 megahertz, but it's not, it's basically running as fast as the instructions can run. And like I said, the next version of the tester, I want to have it running an FPGA with, I don't know, maybe 10 megahertz, maybe 50 megahertz, I don't know exactly, but that would be the capability. Anybody else? Yeah, so a processor chip, I'll reset the processor, I'll essentially single step the clock, and then once I see that there's a memory request, if it's a read memory request, I'll just pass data from an array I already have pre-programmed with some kind of code, and then usually the test checks if it reaches a certain address. And so I'll write a little bit of code that says, jump to this location if it's successful, or jump to this other location if it's unsuccessful, and it'll see what location it ends up on, and that'll determine the result of the test. Anybody else? Yes?
You have an amazing number of chips supported there. How much space do you have left?
With having an SD card plugged into the tester means that space is basically unlimited. Like the actual firmware on the device now, I think, has plenty of room. The device has 1 megabyte of RAM, and if I do, which I will likely do, user-defined tests, you'll probably just have a file on your SD card which has the test information. So it's in theory kind of unlimited how many tests you could put on there. Anybody? Yes? Yeah, so one time I had a chip start smoking. I smelled something. I was like, what's that smell? I said, uh-oh. And that only happened for me when I stuck a capacitor, a bypass capacitor on top of the chip, and I think there was some arcing going on because it was making a poor connection. And that's the only time I've ever smoked a chip. Other than that, so the tester has built-in current limiting. So if I think it's basically like a USB power regulator. I think that's what the chip is designed to be for. But if it detects that there's like over about an amp of current trying to be pulled all at once, it'll just shut down the test, and you'll see on the tester it'll say power fault. Yes?
I'm actually one of your users and love it. That's a great tester.
Thank you.
I was wondering if you would be open to implementing some kind of a EEPROM detection, EEPROMs playing around where they are from, so based on the checksum, you can find.
So I haven't really worked with EEPROMs yet, except on the reading side. I do ripping of ROMs. Obviously, with the new revision of the tester, if I support 20-something volts, I'll be able to program EEPROMs. A lot of the EEPROMs, if you want to analyze them beyond just reading them out like a ROM, you have to apply some kind of high voltage to activate that function. And so that'll be made possible by having different voltage inputs.
What I meant is actually interpreting the content that you find in those EEPROMs and recognizing where it's from.
Oh, you mean like the CRC of the data? Yeah, so I already support reading the CRC of the data, and you can actually put your own file on the SD card with a gigantic list of like SHA-1 checksums and matching names. So that's already something that can be done. And always, like, if you're curious about something, always ask on the forums, because I'm better at responding to requests than I am about having a comprehensive documentation. Anybody else? Yes? So I like synthesizer pop bands from England. Recently, I've developed a little bit of curiosity for some Japanese music from the 80s. Just think 80s, new wave, flamboyant type stuff. Mm-hmm. Anybody else? Yes?
Currently, it's out of stock. Is it temporary, or are you gonna?
So that's because I was reaching the end of a batch, and because I'm here talking about this new tester, like I put together, once I know exactly what I want to do, I can put together a new revision pretty quick. So it was basically like, I don't know if I want to do another batch of the current revision because I'm kind of anxious to get the new revision out. And the main reason I want to get the new revision out is because I want to be able to test those multi-voltage chips. I have some old Fairchild chips I want to diagnose, and they need like minus 10 volts. And also, a lot of people test DRAM chips, and it turns out one of the side effects of doing automated power routing, it introduced a small amount of capacitance, which slowed down the signals, rise and fall time in the realm of about 20 to 50 nanoseconds, and that made some faster DRAM chips or higher capacity DRAM chips not be able to latch addresses. And so I have an adapter for certain kinds of chips. Rather than making 5 more adapters, I just want to make a new revision of the tester. Anybody else? Yes?
What kind of city pop are you into?
City pop. Oh, well, so I got led down the rabbit hole of the Maria Takeuchi on YouTube. And then from that, I became really interested in Chisato Moritaka. And I took a couple Japanese classes at community college, and that's kind of where it left off. But I do have a big curiosity of like synthesizers from the 80s. I like the sounds of the synthesizers they used back then, and I don't know, maybe someday I'll work with old synthesizer hardware. Anybody else? Yes? Say that again? I haven't seen that yet. Oh, if I've dressed up as a samurai? No. All right. Okay. Anybody else? I think we're good to go. All right. Well, thank you so much for attending. Also, if you want to reach out to me, go to my website, BackBit, BACKBIT.io, and you should be able to find a way to contact me on there. Thank you.